So now we can start doing actual designs of reinforced concrete sections. And the first thing you want to do is basically use some general rules to proportion. They're not really code-specific rules, but they're just rules of thumb. So let's say we have a concrete section. How would we even start the design? Well, first thing you need to know is what the span is and end support conditions. So to get the height of the beam, a preliminary height to start with, you would use the span over 8 if it's a cantilever. That's Ln is the clear span. In the Canadian codes they have a table that goes through this. If it's simply supported, you use the clear span over 16. A continuous beam exterior span, Ln over 18, and continuous interior span, Ln over 21. And then that would become your initial trial for H. And once you have that, then you can determine a width of beam. And what you want to do is you want to keep the height to width ratio, this height to width ratio, between 1.5 and 2. And you would start out maybe with a width of, you could start from 250 and then work your way up in 50mm increments for beams. 250, 300, 350, 400. Always keeping in mind this ratio. You want to preserve H to B and also the span ratios to consider. So you would use these three criteria to kind of come up with an initial height to width ratio. And then once you have that, you can start thinking about areas of steel. And the code does give criteria for minimum areas of steel. And what they say is that the moment resistance, MR, has to be greater than 1.2 times the cracking moment. And we've talked about the cracking moment in previous tutorials, how to calculate it. So that gives an indication of minimum area of steel. And that'll be found in clause 10.5.1. This is the A23.304 Canadian standard for reinforced concrete design. And then the area steel minimum, there's a second criteria. AS minimum is equal to 0.2 times the square root of F prime C over F yield times BTH. So F prime C is the concrete strength, and the Fy is the rebar yield strength. And that's in clause 10.5.1.2. Clause 10.5.1.2. But if your moment resistance is in excess of 1.3 times the factor load, 1.33 mF, then you can totally ignore these two criteria, the 10.5.11 and 5.12 criteria, and minimum area of steel will be okay as long as your resistance is greater than 1.33 mF, and that's in clause 10.5.13. Other basic design rules of thumb to use are, something you should always know is that the phi of the concrete, which is the resistance factor that we use, it's kind of a safety factor, is 0.65. So we reduce the strength of F prime C times 0.65. And for steel, it has better quality control, so we use 0.85. And the stress block factors, alpha 1 and beta 1, we'll be getting more involved in these when we actually design, but we'll always use 0.8 and 0.9. They're actually, strictly speaking, a function of F prime C, but no one would fault you for simplifying it down to these two values. Also, a good rule of thumb is for reinforced concrete design, for beams, they generally range from 25 MPa to we can either select 25 MPa or 30 MPa. It really doesn't make a difference when it comes to moment resistance. It's not that sensitive. It's more for other issues, quality issues of the concrete. So you generally choose one of these two in the specs for the strength. Now the true maximum reinforcement ratio, rho max, in the code it says it's limited to rho balanced. And if you don't know about what these terms are, we'll talk about them more. They're in the code when we get to examples. But that's in clause 10.5.2. But I wouldn't use that. I would say that the rho, which is incidentally it's the area of the steel over the width of the web times the depth BD, that rho value should be, you should keep it well below the rho max. If you can, this is a rule of thumb, try and keep it less than 0.5 rho balanced. That's rho balanced here. Should really call it 0.5 rho B. If you can, try and keep it below that value, and also keep the rho value between 1% and 0.35% for beams. It comes with the more economical designs, but they're just rules of thumb, really. And the only other thing to consider would be spacing criteria. So the clear spacing between these bars, if I were to, let's say, blow this up the scale a bit more here, this beam web. So we have these are the ties, or the stirrups, some people call them. I'll draw them thicker. They're generally 10 Ms or 15 Ms, these ties. And what I want to talk about though is the clear spacing between bars. And we call that S. And S, the code says S should be greater than 1.4 times the diameter of the bar to get concrete to work around it. S should be greater than 1.4 times the diameter of the bar, and S should also be greater than 30 millimeters. And also there's a clause for aggregate. But what I always do is I just conservatively say S should always be equal to at least 2 times the diameter of the bar. That's what I use. And that ensures good workability around the bars. But if aggregate is higher than 20 millimeters, then I would say at least 1.4 times the aggregate size. So that should give you an idea for some preliminary ideas when you're proportioning a beam. I just want to also add that I would never use 10 M longitudinal rebar for a beam. A minimum 15 M rebars. And I have a little chart I just put together, and it shows heights of beams, so the height of the beam being here to here. And these are just general rules of thumb again, but if the beam is between 250 to 300 millimeters in height, you probably want to select 15 M, 20 M rebar. For beams in the 300 to 600 range, try selecting 20 Ms to 25 Ms. And then when you get into larger beams, all the way up to 1200 millimeters, you may want to use 25 to 30 Ms. So 1200 millimeters, for example, like a grade beam, you might have a deep grade beam to size, you'd be using these kind of rebars.